So inflection points are points on the curve where the behavior of f changes from one side of that point to the other, specifically where concavity does change. When we change from concave up to concave down, we do have an inflection point. This is the only inflection point on this graph, the only one. Because at this input value, the second derivative is not defined. I can see that. The first derivative isn't defined. My graph takes a sharp curve. There is no derivative there. Therefore, if the first derivative doesn't exist, the second derivative can't exist. But this is only a potential inflection point. It will not be an actual inflection point unless concavity, the sign of the second derivative, does indeed change. So I'm going to come over here somewhere and get a test point and put that test point into my second derivative, and clearly I'm going to get a positive value out. Then I'm going to come over here on the other side of my potential inflection point and get another test point value to put in my second derivative, and clearly it's going to show that it's still positive. This is not an actual inflection point, not an inflection point. If I did the same thing here with this input value, because we always start with potential inflection points, where the second derivative equals 0 or is undefined, I would get the second derivative equals 0 at this input value. I've already tested what's going on to the left of that potential inflection point. Now I'm going to test some value to the right. I'm going to put a test point from this side of things into my second derivative. And since I am concave down, I'm clearly going to get negative out of there. That's what I need to see in order to have an actual inflection point, to be able to do away with potential. I have another potential inflection point here. I've already tested what's happening on this interval. Let's take some input value here, plug it into our second derivative to see what's happening. Clearly, the second derivative is still going to be negative. This is not an inflection point. So hopefully that helps clarify that every time you are asked to find an inflection point, that process is going to look like finding the second derivative, determining where it equals 0 or does not exist, and then actually doing the testing on either side to see if the second derivative does indeed change sign. So here's what an inflection point could look like graphically. Not all of them are going to look like this, but I clearly want you to see that there's just a change in concavity behavior at a true inflection point. We can go from concave up to concave down. We can go from concave down to concave up. Where concavity does indeed change is the actual inflection point. It's very important that you do the testing to determine that the sign of your second derivative did indeed change. We went from positive output values here to negative output values there. This example, we went from negative output values to positive output values. If I was graphing in the plane the second derivative function, the only way that outputs can go from negative outputs to positive outputs is if we crossed the x-axis, that's where your function equals 0, or if we jumped the x-axis. We don't necessarily have to cross it, but we could jump it. That would look like where your second derivative did not have an output. Yes? So that's why we're testing on either side whether we actually change the output from negative to positive or positive to negative on the second derivative function. Find all inflection points of the graph of f of x. So here's the process. The process is find the first derivative. I don't need the first derivative. I'm not going to answer any monotonicity questions, but the only way that I can get to the second derivative is to go through the first derivative. So the derivative of the first term, the 3 pops down front. That leaves me a coefficient of 1/2. Reduce my power by 1. There's the first derivative function. The second derivative function, 2 pops down front, 1/2 times 2 is 1. I don't write times 1. Reduce the power by 1. The derivative of a constant is 0. So the second derivative is the function y equals x. That derivative, that function f double prime, will equal 0 only when x equals 0. And the function is always defined. I don't have to worry about any values where f double prime might not exist. Don't forget to look for those potential inflection points as well. But y equals x is a smooth continuous function, no holes, no jumps, no vertical asymptotes. I've only got 1 0. So I have, or we have, one potential inflection point. I don't know if it is an actual inflection point until I do some testing. Here's what our testing looks like. We're going to clearly label for the AP reader so that they know, we know what we're doing. I'm going to plug my test points into my second derivative function. When I plug a negative into y equals x, I get a negative out. When I plug a positive into y equals x, I get a positive out. Concavity does change. When that happens, because my second derivative changes sign, I just verified that I'm no longer dealing with potential. F of x has one inflection point at x equal 0. There we are. So make sure you understand what the second derivative tells us about the concavity of the original function f. Also, what the second derivative tells us about the first derivative, f prime. Know those relationships in both directions. And make sure you understand there is a difference between potential inflection points and actual inflection points. You must do the testing to determine whether concavity changes. If concavity did not change on this function would not have any inflection points. However, it did, at the one potential inflection point, x equals 0. Therefore, that became an actual inflection point.